Okay, this lesson we're going to be looking at Unit 2, Chapter 1, Function Transformations, and we're going to be looking at Reflections and Stretches, Part 2. Okay, this lesson will focus on finding the equation of a function whose graph is a stretch and or a reflection of the graph of y equals the f of x. Example 1. Let's write the equation of a transformed function. So we're going to be given the graph of a transformed function, and we're going to be looking for the equation of the transformed graph. The graph of a function y equals the f of x has been transformed by either a stretch or reflection. Write the equation of the transformed graph g of x. So here's the original function, f of x. Here's my new function, g of x. First of all, is it a stretch or reflection? I think if you look at the graph, we can clearly identify this as a stretch. We need to determine the type of stretch that has occurred, and let's write the equation of the transformed graph. In this particular case, there are two scenarios that we need to consider. We need to consider case 1 is if the graph has been stretched vertically by a certain factor. So let's consider, first of all, a vertical stretch. All we need to do is find a couple of points on the graph that represent a vertical stretch. So let's take, for example, the point right here on the original graph, which is the point 2, 2. And if we move that point vertically, you can see that that point vertically has been moved right there. So the point 2, 2 has been mapped onto the point 2, 6. Let's find another point, and let's see if the same result occurs here. We got the point 4, 4. Where would that point be located vertically on the new graph? Vertically on the new graph, that point is now at 4 and 12. If you compare these points, the point 2, 2 has been mapped to 2, 6. That would be a stretch vertically by a factor of 3, because the 2 times 3 will give us 6. Is that the same for the other point? 4, 4 is mapped to 4, 12. Again, notice there's no change in the x-coordinate, but the y-coordinate has become 3 times larger. So as a result, we have a vertical stretch of 3. And again, simply look at the fact that we're multiplying by 3 and we're multiplying by 3. So we end up with a vertical stretch of 3. We need to write the equation of the new graph. The equation of the new graph, g of x, will be this. The g of x will equal stretch vertically by a factor of 3. 1 over, delete that. A vertical stretch of 3 will simply be 3 times the f of x. Or I could write it as 1 over 3 g of x equals the f of x. Either of these are fine. That's a vertical stretch of 3 units. Case 2, we need to consider what if the graph has been stretched horizontally. Let's consider a horizontal stretch. If we need to consider a horizontal stretch, let's look at some points on the graph and figure out where those points have been moved to horizontally. Let's take these 2 points here. You can see that horizontally, the point on the original graph is the blue graph, is negative 6 and 6. And that's been mapped to negative 2 and 6. Let's find another couple of points that have been moved horizontally. That's not a good example. Let's choose this one here and here. That's the point negative 8, 10, 12. Negative 12 and 12 has been moved to negative 4 and 12. Now let's compare the points. There's no change in the y value. What has happened to the x value in both cases? You can see that it's a horizontal stretch now of 1/3. A horizontal stretch of 1/3. if I multiply this by 1/3, I will get the other point, or the other coordinate. -6 times a third is -2. -12 times 1/3 is -4. So we end up with a horizontal stretch of 1/3. In the equation, it would look like this. There's only one way to write this. It's the f of 3x. That's a horizontal stretch of 1/3. There's the equation for the g of x. Either one of these would be fine. It didn't ask for both, but we decided to do both. I could represent it like this, or I could represent it like this, and of course both of these being the same. Okay, let's have a look at another example. The graph of the function y equals the f of x has been transformed by either a stretch or reflection. Write the equation of the transformed graph, g of x. Well, I think if you look at the graph of the f of x and the graph of the g of x, we can clearly see that there's a reflection occurring here. And the reflection occurs in the x-axis. So if there's a reflection in the x-axis, the new function, g of x, of course, is simply the graph of the f of x with a reflection in the x-axis. We end up with a negative placed right here. Reflection in the x-axis, or I could write it like this. The g of x, negative g of x equals the absolute value of x. Either one of these is fine. Both of those represent a reflection in the x-axis. Let's have a look at a couple of multiple choice relating to this topic. What transformations occur when the graph of y equals the f of x is transformed onto the graph of y equals the g of x? Here's the original function. Here's the new function. What type of transformation has occurred? Do we have a vertical translation of 1 unit up, a vertical translation of 1 unit down, a vertical stretch of 1/2, or a vertical stretch of 2? The way I suggest we do this one is to look at the distance between 2 points vertically. You can see here that this graph hasn't been translated hasn't been translated vertically because the shape of the graph has changed. So it has to be a vertical stretch. So what we simply need to do is find the distance between 2 points on the graph. So let's choose these 2 points right here. And you can see the original graph, the distance between those 2 points is between -2 and 8, which is 10 units. Let's find the distance between the exact same 2 points on the other graph. The distance here is between -1 and 4, which is 5 units. So the function f of x has a distance between 2 points of 10. The new function g of x has a distance between the same 2 points of 5. That would represent a vertical stretch of 1/2. The graph has been stretched vertically by a factor of 1/2. The graph is smaller, so it's been stretched vertically by a factor of 1/2. Let's have a look at another example. Which graph represents a transformation of the function f of x equals x squared with a mapping rule of xy maps to x comma -5y. Now, x comma -5y, there are 2 transformations here. Let's identify them. The negative here indicates a reflection in the x-axis. And of course, the 5 represents a vertical stretch of 5. Vertical stretch of 5. So we're looking for a graph that has a reflection in the x-axis and stretched vertically by a factor of 5. If you think about the original graph. Now, the original graph is a parabola opening upwards, right? With its vertex at the origin. So let's just look at the original graph. Let me just do a quick sketch here of the original graph. 2 and 4 is a point on the graph, -2 and 4 is a point on the graph. So here is what the original graph looks like. Something like that. Now, we need to reflect it in the x-axis. So clearly, it has to be either A or B, because both of those have reflections in the x-axis. C and D actually have reflections in the y-axis. So it has to be either A or B. And it's stretched by a factor of 5. Which of these do you think is stretched by a factor of 5? The answer is D. This one is stretched by a factor of 5. And I think we have one example left, right here. The graph of the function y equals the f of x has been transformed. Write the equation of the transformed graph g of x. Very similar to the first example we did. This can be represented two ways. Let's look at the two cases. Case 1, let's consider it as a horizontal stretch. And case 2, let's consider it as a vertical stretch. All we need to do again is find points on the graph and figure out where those points have been now located once they've been transformed, and from there we should be able to figure out the horizontal and vertical stretch. Okay, we got to look for some key points here. Let's take this point here and this point here. Again, the original function is this one here, remember? So we've got to be looking at a case where we got the point 2, 4 has been mapped to 1, 4. 2, 4 is mapped to 1, 4. Let's see if we can find two other key points on the graph. See if that will help us. What about these 2 points here horizontally again? The point 4, 16 has been mapped to 2, 16. Now, let's look at what type of horizontal stretch has probably occurred here. Hopefully you will agree that it's a horizontal stretch of 1/2. If I multiply that by 1/2, I will get 1. If I multiply the 4 by 1/2, I will get 2. Notice there's no change in the y-coordinates, so we've only got a horizontal stretch of 1/2 here. That's one scenario. Case 1 is a horizontal stretch of 1/2. Let's write the equation with a horizontal stretch of 1/2. The g of x equals the f of horizontal stretch of 1/2 would look like this. The f of 2x. That's a horizontal stretch of 1/2. Case 2, let's consider a vertical stretch. Let's take some points on the graph and let's see where those points are now located with a vertical stretch. There's a couple points. So the point -2, 4 has been stretched to -2, 16. I think you'll agree that this represents a vertical stretch of 4, because I need to multiply by 4 to get the next number there. From 4 to 16 would be a vertical stretch of 4. So we have a vertical stretch of 4. I can write that like this: 1/4 times the g of x equals the f of x, or I can write it like this: the g of x equals 4 times the f of x. There is again a vertical stretch of 4. Key ideas. To find the equation of a translated graph, we simply locate a point on the graph. We find the corresponding point on the new graph, the translated graph. We determine the reflection or the stretch that has occurred to move from the f of x to the g of x. And we insert the reflection or the stretch into the appropriate equation below. Of course, both of these represent both of these represent reflections, both of these represent stretches. So you just insert it into the correct equation. That ends today's lesson, and we're done.